Okay, right now I want to talk about the answers to homework set 4, which I posted on Blackboard. You can see whenever you want, but I've recently graded these homeworks, and I noticed that there were some consistent misunderstandings, more so than I realized at the time in some of these questions, and I think it's worth it to just go over them a little bit, like sort of what I expected you to do. And this first question says, use the implicit function theorem to show there exists an explicit function z in a neighborhood of 0, 5, 1. And most people got this idea that what you wanted to do was take the derivative of this implicit function with respect to z and just make sure it's not 0. That was good. I sort of thought each of these, there's 5 parts of problems. I think of them as being 2 points each. So you got almost all of the credit for this problem by saying that, but I wanted you to say something more, and that is, I wanted you to say the implicit function is continuous and differentiable. You can really just say differentiable at the point in question. So at this point, 0, 5, -1, this function here is perfectly differentiable. Differentiable means that the derivative exists. Whereas that's not always the case. In fact, if you have an implicit function whose derivatives or partial derivatives do not exist in a point, in a neighborhood of a point, then you can't use the implicit function theorem. So a lot of you just wrote out this f of z and equals 3, and that was it. That was all you wrote, like one line of writing, and you were very, very brief. And I'm okay with brevity, but when you leave out one of the assumptions of a theorem, I had to take off just a little bit. I'd like to take off 1/4 of a point out of 2 if you did not mention this other part of the implicit function theorem. And I know maybe when you're looking at my slides, maybe I don't write it in the slides very often because maybe I just say it in my words. But yeah, you can't use the implicit function theorem unless the implicit function that you're dealing with is differentiable in a neighborhood of the point. Okay, in question. So other than that, you guys did pretty well. And then when you get this one, some people did like dz dx. No, it was dy. You got to look right here. It says y, not x. Just be careful, I guess. It's my advice to you. And then you need to remember here, dz dy is negative fy over fz. Some people actually saw the negative and then forgot about it, or they just totally forgot about this negative. But once you plug in, what do you get? 3 for f of z and -1 for f of y, plus these negatives cancel out. The answer should be 1/3. Some people's got -1/3, 1/3. Most people did okay with 1b. Most people did okay with 2a. I got a little bit strange answers. Sometimes you actually had a y on both sides of this equation here. You just get this by however you want, plugging in, solving this for c and plugging it in. You actually get y's on both sides of this equation. And if it were me, I would cancel out the y's. I think that's the best algebraic thing to do. If you left the y's there, I said, okay, that's fine. You can leave the y's in. And if you didn't change the y's to y stars, that's okay too. I didn't take off points for that. But you should have something that looks like this. Of course, these could all be, it could be negative, negative, positive, positive. That's fine too. You could have a y on both sides, but you needed something like this for part A. It was just combining these two equations using substitution. That's all I had to do, and change the y's to y stars. Okay, so for 2b, there was a lot of problems, and I think I've already talked about it. But now that I've graded your homework, I see exactly where people made the problems, and that was you need to use the implicit function theorem. And I don't think people were. They were just like talking straight on about y dy. They started to like calculate dy dg0 here, and that's actually not what's being asked. Just to show that the explicit function exists, you should calculate Well, so the point is you have to use the implicit function. That's all you have, the one from part A. So you have an implicit function of y and g0 because y star and g0 both exist in this implicit function. That's really all you have to go by. You have to take the derivative of that with respect to y star. I don't think everybody was doing that. You had to take the derivative of this left-hand side of this equation with respect to y star and show that that's not equal to 0. I also think people were being very, very casual when they're using this theorem to not even say what it is the theorem requires. I'm okay with you being informal in some ways, but like when you're writing out your homeworks, or especially when you're doing a quiz or an exam, make sure you're saying at least a little bit what it is you're doing. Somebody who's reading it should be able to tell what it is you're doing. Whereas if you just write something like, I don't know, there's a little English explanation that needs to go along with the math sometimes for someone to be able to follow what it is you're doing. I just think some people, maybe they were confused, and that's part of the reason you didn't write very much words, is because you didn't really understand what you were doing. But I think you can understand what you're doing. I think especially if you do understand, write a little bit more to me, the person reading it, so that I can tell you understand what you're doing. So in this case, what do you have to do? You have to show that f y star is not 0. That's how you use the implicit function theorem to show an explicit function exists. And it's particular this, not dy dg 0 equal to 0. I'm not sure why people had that. That's not what you're looking for. You're looking for the derivative of this entire implicit function with respect to y star should not be equal to 0. Well, what is it? It's just the derivative of this first term is t prime. The derivative of this second term is s prime. The derivative of this third term is I prime. The derivative of g0 goes away. There's no y there, so it goes away. Once you have this t prime plus s prime plus I prime, you have to show that it's not 0. Even some people just stopped there. They stopped there. Even if they got that, it's like, oh, good, you got that. That's not the whole thing. You still need to use some kind of argument. By argument, I don't mean like you get into a fight and you're punching the other person. It just means you're using logic to explain why it's true. And why it's true that this is not equal to 0, you have to use this assumption here, the one from the problem. And a lot of people, I think, just missed that. They missed that in the problem. I'm telling you that s prime plus t prime is greater than I prime. You have to, sometimes the word is invoke. You invoke this assumption. It's the very last thing I said in this paragraph of the problem, but it's kind of the most important thing. S prime plus t prime is greater than I prime. What does that tell you? That tells you that this part here, t plus s, is greater than this part, I prime in absolute value. That means the whole thing is positive. You have a larger positive number than this is a negative number. That means the whole thing has to be positive. You don't really care that it's positive, but you do care that it's not 0. So try to remember that. What's my advice? I should be giving you advice how to solve problems like this. Remember what it is you have to work with in the problem. And these assumptions that it's easy to sort of ignore them, like, okay, that's just some meaningless stuff that's part of the problem. Sometimes there's really relevant things in the problem that you need to use. So don't forget to maybe read the full text of the problem, what I've written here, and remember that some of that information could be valuable for you to solve the question. And don't forget to use words to kind of say what it is, the theorem that you're invoking, what it is that it does. Because I think like a lot of times people just wrote something. I think you were guessing. I think you didn't know what to do, so you were guessing. But what I would hate to have happen is if you actually did know like what the implicit function theorem was, and you did have some idea of how to use it, but you just took it for granted or something and wrote something that I couldn't tell. I couldn't tell that's what you were intending to do. I would hate for that to happen. I want you guys to get as much credit for these problems as you can. So just be careful in the future when you're writing. And especially a question like this is like a show that question, right? Show that, if you answer with an explicit function, y star must exist. Okay, but you should have showed it somehow, right? There should be sort of logical flow to what you've written, what you've said, so that me, the person reading it, can tell, oh, given the assumptions that we started with, I can use logic to arrive at the conclusion that I wanted you to arrive at. That's what these problems should have, and I think it was missing for most of the class. So, I mean, don't feel bad if you didn't do it, because a lot of people didn't do it. I think in the future you will be able to, hopefully. Okay, this move on. This is the last one too. People maybe tried to find dy dg 0. I once again think somehow they were confused and thought it was equal to 0 in some case, but I wanted you to determine its sign. That means tell me whether it's positive or negative. Some people actually calculated it, but didn't tell me whether it was positive or negative. That's certainly part of the problem. I did say to find it, but then the second half was determine its sign. Do both parts of the problem. That's another suggestion I have, is to read the whole problem too. Read the whole question. I'm not just asking you to find dy star dg 0. I'm asking you to tell me whether it's positive or negative. And you can do that. Once again, you need to invoke this assumption of the problem. The assumption was s prime plus t prime is greater than I prime. You needed to use that in order to tell that this denominator was positive. And then you have a negative sign over positive. That means the whole thing must be positive. Yeah, this is using, I think a lot of people got something like this. They knew that you were supposed to use the corollary of the implicit function theorem. So they had something like this, but they didn't go the full mile to calculate the sign of the IFTC. So hopefully I still tried to give you guys partial credit. There were some answers here that frankly were kind of bad. I usually compliment you a lot on the homework. I say, oh, you guys did pretty well in the homework. But for homework set 4, I think there clearly was some misunderstanding. But despite that, I tried to give you a lot of partial credit, like sometimes 1 out of 2 points, or at least a half out of the 2 points, even if there really was very little for me to tell what it is you were doing. That's another suggestion. You will get a lot of partial credit in this class if you can at least show me some understanding of how you would solve this problem, like making progress on the problem and writing that down and showing that to me. It's like almost always a good thing for you as a student. I recommend you do that. And as clearly as possible, because if I can tell what it is you're doing without a lot of just sort of, I don't want to say random, that sounds bad, but I'll say unorganized mathematical thoughts and ideas all being put down on the paper, and maybe a lot of it's irrelevant, sort of a lot of noise going on in your answer, that's probably bad for you. It makes it seem less like, I mean, if you get the right answer, I'll probably give you full credit anyway, even if you did write some noisy stuff on your paper. But if you didn't get the right answer, now I'm looking at how much partial credit should I give you? And if what you've written is a lot of noise and just a little bit of actual progress towards the answer, I would probably give you less partial credit than if you just had stuff that was logical and made sense towards getting the answer. Sorry, guys, I don't mean to be critical of you, especially you guys who are here. I'm just trying to help. I hope in the future, get you some more points. These classes and other classes too. I'm not the only economics professor you're going to have. I'm sure there will be some other people who also these sort of test taking tips and homework taking tips may help. Okay, guys, you guys have any questions about homework set 4? I posted the answers so you can see them there. I guess. Oh yeah, go ahead, Kai.
I said no, I don't have any.
Oh no. Okay. All right. So now I have homework set 5 to grade too. I shouldn't be taking so long, but I'll try to do better on homework set 5. I think there'll be at least one more homework, and there is a quiz. In case you just came here, there will be a quiz on Thursday, and the quiz will be over more constrained optimization problems. I might make it a little bit harder than the one you had on your homework, or at least, change something. Or maybe I'll add the second order condition that you have to tell me about. That's the kind of thing I could ask in multiple choice. I actually like multiple choice questions because the computer will grade them for me. Blackboard grades the multiple choice for me. I only have to grade the essay questions or just the essay questions. So probably expect that too. I'm going to ask you, I'm going to give you a problem. I'm going to say, what's the answer? And check the second order conditions. Sometimes I say, don't worry about the second order conditions. But for this quiz on Thursday, I'll say, please check the second order conditions as well. What are they? Let's do them. Let's talk about them now. Hey, and before we do that, can I give you a motivating example? This is what I call an example to motivate what I'm going to be talking about. So let's have that. I'm sorry, I'm going to use my whiteboard again. I know it's terrible. Let me assume that I'm giving you this problem, and that is to maximize over x and y both have to be, let's say, not negative. It can be 0 or positive. And the thing I want you to maximize is this something that might kind of look like a utility function. We'll say x squared plus y squared. And I'm going to give you a constraint. Make it I want this to be as simple as possible, such that something like x plus y equals 10. This is like a very simple budget constraint, maybe a very simple utility function. You may think, oh, I've done a million problems like this. This is really easy. And let's talk about how you would use the method of Lagrange multipliers to answer this. You would say, okay, the Lagrangian function, right, is equal to the objective function x squared minus y squared plus the Lagrange multiplier, which is it doesn't exist yet. You're creating it, lambda times the constraint written as the right side minus the left, which is 10 minus x minus y. You guys remember this? This is like the first step in the method of Lagrange multipliers. It's just to write out L, the function. Sometimes the book calls it Z, but I call it L. Right? You with me?
Yeah.
Thank you. Thank you, Kai. I need that little validation just to make sure I'm not screaming into the void with no intention. Okay, so now let's think of the first order conditions here, and that is sometimes you just write here Lx. It's like the derivative of L with respect to x. I'm going to do it so it goes quick. 2x, and then I have a minus lambda here. That should be equal to 0. Another quick way to write that is that, isn't it? 2x, and here I'll even write that as a name. Ly, from Ly, what do we get? We're going to get actually the same thing. 2y equals lambda, aren't we? If we use these two to combine lambda, I'm doing this fast because I'm trying to make a point. It's to say, okay, and will 2x equals 2y, divide both sides by x by 2, you get x equals y, don't you? X equals y. If I plug that into what would be the third first order condition, I would get, instead of x plus y equals 10, I would get x plus x equals 10, because x equals y. I'm substituting y into there. X plus x equals 10. That means x equals 5 and y equals 5. And this looks like an answer, doesn't it? What do you think? X star equals y star equals 5. Answer. Done? Are we done? Kind of looks right. Right? We're trying to maximize something that looks like a utility function, given something that looks like a budget constraint. And what do we determined? Well, I don't know. Let's set x star equal to y star equal to 5 and say, there we go. That satisfies the that satisfies all the first order conditions of the Lagrangian equation.
Professor,
Yes.
why wouldn't the partial derivative for y be negative 2y?
Oops. That was supposed to be a plus.
Okay.
Thank you for bringing that up. See, here's a plus. Then when I wrote it here, it looked like a minus, doesn't it? How's that?
You said -2, so okay.
I said minus. Did I say minus the first time?
Yeah, that's why I was kind of confused.
So I've said minus the whole time. I apologize. No, I meant x squared plus y squared. Who's this, Jonathan?
Yeah, sounds
Thanks,
good.
Jonathan. No, that was just a mistake in a transcription. So I had this example in mind the whole time. I wanted it to be x squared plus y squared, and I wanted this to be x plus y equals 10. If I said anything different, that was just a mistake. But regardless, but anyway, thanks for bringing that up. But what I've circled in red, is that the answer? What do you guys think? Deshaun is here with an iPhone. What do you guys think? Is that what I've circled? Is that the answer to this problem?
Yeah, I know we have a basic oversight, like the listening session, like basic session. So
Is this person talking to me? I don't think so.
Yeah.
Is someone talking?
Yes.
Because I can't hear him.
I think it was someone's TV or something. Or
Yeah, it's like a
something in the
TV or
background.
something. Somebody's watching Netflix on the side. Watching Bridgerton. Come on, guys, it's class time. Kai, you think yes, it is the answer?
Yeah.
Okay,
Yeah.
because it satisfies all the first order conditions, doesn't it?
Yeah.
And that's what I've been teaching you. Hey, you want to do a constrained optimization problem? I've got just the method for you. It's called the method of Lagrange multipliers. You create this Lagrangian function, which is equal to the objective function plus the Lagrange multiplier times the constraint. You take the derivatives of all of those. You get a system of first order equations, and when you solve them simultaneously, you get the answer. Sorry for speaking so quickly, but yeah, based on what I just said, you would think this is the answer. X star equals y star equals 5. It's not. It's incorrect. And so I will make sure, I probably won't. I should make sure that this is not my thumbnail on the YouTube video that eventually gets made for this lecture, because this is incorrect. Think about it. If x and y are both 5, what is our objective function here? I mean, let's do some arrows here. What would our objective function be with this? This would mean our objective function is 5 squared plus 5 squared. That's 25 plus 25. That equals 50. Right? What if, let me just ballpark in here. What if I, instead of this, I said, how about if I let x star equals 10? X star equals 10. And a y star equals 0. What if I just try that one instead? What'll happen? You know what I'm going to do? I'm going to use green. I'm going to use green to circle this one. And once again, I'm thinking like red X and green check. It's better, isn't it? It's better. I want an arrow. An arrow. What will this get me? This will get me 100. So what's happening here? why did we basically find 50 when 50 is not the maximum? In fact, I could choose 100 and it's better. This is actually a maximum, 100. Or I could flip it, x equals 0, y equals 10. That would also give me 100. There's two maximum values for this problem, and that's either x equals 10 or y equals 10, and the other is 0. Okay, I'll just tell you the point. This is a minimum. This value that I found in red is the minimum. And of course, if you look here, the word is max, not min, it's max. So what if you do this problem and you think you're finding a maximum? In fact, everyone sort of did. I mean, no offense, but nobody in the class was like, no, that's not a max, that's a min. I probably had you fooled that actually this is a max. No, it wasn't. You may not really be able to tell very easily. That's where the second order conditions will come in. The second order conditions will say, these will satisfy the second order conditions for max, right? The second order conditions for maximum will be satisfied for this, although it'll be a little weird because it's a corner solution. So but the second order conditions for minimum will be satisfied for this one. Okay, check. But for max, they won't. All right, so let's talk about what the second order conditions are. Isn't this a good motivating example? This is an example which motivates us to care about the second order conditions so that we don't fall into a trap like this. Let me put up I think I have the slides. Where are they? They're in course documents right now. I'm going to go to Lagrange multipliers and constraint optimization. Open Lagrange multipliers and constraint optimization. Maybe I need to stop share so I can share the right thing. Here it is. Okay, so let's look at the slides. I can even do full screen, I think. F11. F11 on a PC is full screen. This is stuff we've already done. Stuff we've already done. Here we go. By the way, this was the end of the previous example of the Lagrange method. And we got this answer, and I said, is it the solution or not? And I didn't tell you the second order conditions. We just said, yes, it has to be the solution. It's the only possible max because the corner solutions are clearly worse. And there has to be some maximum, and this is the only chance that it could be. Okay. But now we don't want to just wave our hands. We want to use math to say what the second order conditions are. Remember, I'm going to ask you about it on the quiz on Thursday. So hopefully you pay attention here. This is the second order condition for a constrained maximization or minimization problem. I'm giving you both. The constrained optimization problem doesn't have the same looking second order condition. It doesn't just have a Hessian. I'm going to annotate now. I like annotating. This thing I have here in red, not the whole thing, but just this thing here in red, that is the Hessian matrix. Okay. So it's like we're going to take our usual Hessian matrix, which are simply the second order partial derivatives of the objective function f. That's here, this little part of this matrix. By the way, this matrix will be called H bar. If you're thinking of how should I speak of this, you could either call it the bordered Hessian, or if you want a quick name for it, H bar is fine. And the way you write the bordered Hessian, the way you construct it, is to say, make a little matrix here of the Hessian and add to it. What will you add? One row, the first row, and one column, the first column. So the first row and the first column are a little bit special here, especially in that the first element should be a 0. it's like automatically the row 1, column 1 entry is just going to be a 0. That's sort of just by definition. You might ask, why is it a 0? There's a deep answer to that, I'm sure, but it's sort of irrelevant. It's just by definition, that's how this H bar is constructed. If you look at the first row, you get the partial derivatives of not the objective function, but of the constraint, where, if you write the constraint this way, it's essentially, it's a function. It's a function of your choice variables, x and y in this case. And you take the partial derivative of this constraint function, we call it g, and place those as the elements of this first row. Well, there should be 2. There should be 1 for each choice variable. If for some reason there were 3, it would be like gx, gy, gz. But then the Hessian would grow too. It would be fxx, fxy, fxz. So there's always the same number of partial derivatives of g as there are this first row of the Hessian. So that this will always fit. And that's what you do for the first row. And you similarly do the exact same thing in the column. You simply write the partial derivatives of not the objective function, but the constraint function there for gx and gy. So that whole thing, I'm going to clear my drawings. This whole thing is called the bordered Hessian H bar. And I've constructed these problems. I'm only going to give you the 2 choice variable one, I believe, for this class. If you want to go to grad school, go to take my class or the equivalent class at the master's level. We'll do this more generally with like any number of variables, and you'll have to know the rule in general. But for this class, just know these 2 rules. These 2 rules are good enough. If the determinant of this bordered Hessian is greater than 0 at a critical point, then you found a constrained maximum. Why don't I just say maximum? It's basically the same. Constrained means given the constraint, it's a maximum. That's what that means. Okay, it's greater than 0 for a maximum. If the determinant of this bordered Hessian is less than 0 at a critical point, then it's a constrained minimum. That's it. Note that this is flipped. Don't get confused here. This is flipped. It's like backwards from what I've been telling you. From the unconstrained optimization, SOC. These guys are jerks. Whoever invented math, they're trying to confuse you by flipping which one is positive and which one is negative for the min or max. I have to say they're not jerks. They didn't do this. They didn't do this to confuse you. This is just the nature of the universe dictated the second order conditions for these types of problems. It wasn't anybody scheming somewhere when they wrote a textbook. So you get what I'm saying here about flipped? In the unconstrained SOC, you wanted the Hessian. So actually you wanted the determinant to always be positive, but you wanted the first element to be negative for a maximum, and you want it to be positive for a minimum. It's flipped now, so that you want, now it's actually, you're talking about the whole determinant of the Hessian, the bordered Hessian. So it's already a little different. The word flipped is a little questionable here. Is it really flipped? It's not necessarily flipped. It's more like it's a totally different interpretation of what do you do with the Hessian. In these types of problems, I'm not just looking at one element. I'm taking the determinant of the whole thing, and if it's positive, it's a maximum. If it's negative, minimum. Okay, let's go back and look. Is it okay if we? Did anybody have any questions about this? It's okay if I ask you pretty much a multiple choice question about this on the quiz tomorrow. Okay, but let's. Do you mind if I go back and share what I had on the whiteboard? Here we go. I think you can see it right now. You see the whiteboard? Sometimes it doesn't work so well.
Yeah,
you
I
can
see
the whiteboard. Great. let's try to find the bordered Hessian for this problem. And I want to keep as much as I can of it. I just erased those. I think that's okay. Yeah, I don't care about this. I'm gonna look at the min one and sort of convince myself that yes, it is a min. Let's write out the bordered Hessian. I call it H bar. H bar equals, it's going to be a 3 by 3 matrix. The top left, do you remember what it is? Goose egg, 0 there, top left. How about the first row? What should I put there? The first row of the bordered Hessian. It's a 0. What comes after the 0? You remember? It is the partial derivative of the constraint function. The constraint function is x plus y equals 10. So I want the partial derivative of that. You can just look at the left side of it. Assuming that the right side is a constant, just look at the left side of this and take the derivative with respect to x. It's 1. Agreed? Amina, you have a question, or were you just going to answer?
No, that's what I was going to say.
You're going to say 1. It is correct. That's correct. It's 1. And the second element, or sorry, so the row is 0, 1, 1, because the partial derivative with respect to x is 1. The partial derivative with respect to y is also 1. I'm going to close this matrix here. And going down the first column, those are also 1s. That's symmetric this way. This is a symmetric matrix, by the way, so it'll always be symmetric. What goes here is the second derivative of, you know what, I'm forgetting now. Did I said it was of the objective function, but I'm having doubts that I think maybe it should be for the entire Lagrangian. That would be bad. So it sort of doesn't matter in this case because this is all first order stuff, so it'll disappear in the second when you take the second derivative. But I'll make sure about that before anything happens for next class. I'll confirm that second order condition for you guys. I'll make sure what I have on the slides is right, essentially. But okay, to fill out this part of the bordered Hessian, we want the actual Hessian of this x squared plus y squared, and that is the derivative with respect to x twice. What will that be? I will get 2x, then I'll get 2. It's simply a 2, isn't it? 2. How about here? This would be the derivative first with respect to x and then with respect to y. That will be, first I get 2x, and I take the derivative of 2x with respect to y, it disappears. It's 0. You guys agree? You guys agree with this?
Yeah.
Thanks. These are 2's because x squared becomes 2x becomes a 2. Y squared becomes 2y becomes a 2. These are 0's because there's no term with both x's and y's in them. Okay. So what do I want to do? I want to take the determinant of that Hessian, bordered Hessian matrix. Do you remember how to take determinants? I taught you this back in the first half of the class. 0 times, so it's going to be 0 times a bunch of stuff. Who cares what it is because it's 0. Now I'm going to subtract, because I'm going across this first one, I'm going to subtract the 1, alternating sign, so that's why it's -1, times the determinant of this submatrix created by eliminating the row and column of this 1, and that is 1 times 2 minus 0, that's 2. Okay, and now the final term will be a +1, the matrix here, which is 1 times 0 minus 1 times 2, that's a -2. That's what I get. Tell me if I'm wrong, but that's what I get. 0 minus 2 minus 2, I get -4, which is less than 0. And remember, it's this is a good way to remember when you're doing a problem like this is, what does that mean when it's negative? Oh, it's flipped. Used to be that negative was for a maximum, but now negative is for a minimum. So this tells me I have satisfied the second order conditions for a minimum. This red, what I've circled in red, I already knew that, right? I told you that before we even started, that this is not a maximum, it's a minimum. The bordered Hessian second order condition tells us that because this is less than 0, okay? If instead you had done this correctly and found that H bar has a determinant which is positive, then you could reasonably conclude, rightfully, you could conclude that the critical point you found is a maximum. But in this case, it was a minimum. You guys see that? See how that works? I think in some cases it's actually cleaner than the one for unconstrained optimization. For that one, you sort of have to check two things, and it may be a max, it may be a min, or it might be neither. Whereas in this case, as long as the functions are smooth, if you find a critical point, it will either be a max or a min. I guess that's not true. If the determinant is equal to 0, then you might say, oh, it's definitely neither. That's false. Actually, if you find the determinant is equal to 0, it means the test is inconclusive. It might be a max, it might be a min, it might be neither. You just don't know. I think that's true. I think I'm right about that. You guys can check me. Okay, stop share. What else do you want to do today? Let's maybe another example. Oh, by the way, yeah. So returning to example 1. Example 1 was this problem. It's like a, sorry, it's a consumer optimization problem, right? Where we had utility function, we had a budget constraint, and I asked, what's the utility maximizing choice of X and Y? We got this Lagrangian, and we did the first order conditions, and we got the answer. When we solved the system of first order conditions, we got this answer 40/3 and 50/3. What I'd like to do now is go back and verify that that's indeed a maximum using the second order condition that we have. So let's return to this problem. Find the bordered Hessian. Wait, yeah, let's do that. Let's do that right now. This will be more practice with finding the bordered Hessian. I'm going to annotate. H bar, maybe you guys can tell me what it is. Is it going to be a 3x3 matrix? What will it look like? Give me the first row.
0, 5, and 2.
Very good. Thank you, Jordan. 0, 5, 2. You guys see how we got that? Those are the 0 is just always 0. 5 is the derivative with respect to X. 2 is the derivative with respect to Y. He's correct. And we know it's symmetric, so we can put that 5, 2 down here as a column as well. How about here? What goes in the center of this matrix? Not necessarily as obvious as it was before. We have X squared Y here. You want to take this derivative with respect to X twice. What will you get? And we have an answer? What is fxx? What?
Would it just be 0 for that one?
Good guess, but no. There's going to be a term here. So what's the derivative with respect to X? It's going to be equal to X squared Y becomes 2xy, doesn't it?
2xy, that's why.
2xy. So if I want fxx, what does it get? What does it become?
2y.
It's 2y. Very good. 2y. That's what should go here. And you might say, what? I thought they were always numbers. No, they just happen to be numbers. They can be variables here too. And you know, what do you do when you're evaluating the second order conditions? If there's variables here instead of just numbers, you plug in the X star and the Y star that you found using the first order conditions. That's the whole point of a second order. When you say second order, it means you only look at this after you found something that satisfies the first order conditions. That's what that means. A lot of people think it means the second derivative. No, it happens to be about second derivatives, but that's not what the order means. Okay, how about fxy? What's that one?
2x.
2x, very good. And remember, it's symmetric, so I can put that here too. How about fyy?
Zero.
Thank you. That is correct. 2 fyy is 0. So we believe this is what the bordered Hessian looks like. And we wanted to find what do we want to do? We want to confirm, for the sake of illustration, that the answer that we found for example 1 is indeed a maximum using the bordered Hessian. Well, we can't exactly do it here unless we know what x and y are and we plug those in. I believe I have that on the next slide though. So I'll show it to you on the next slide, okay? I'm gonna clear these drawings. Unless you had any questions for that. Yeah, that's what we got. Exactly the same Hessian. To go the distance here though, we need to plug in what x and y are, and I already forgot what they were. There's something like 40 thirds and 50 thirds. Was that it? Yeah, x equals 40 thirds, y equals 50 thirds. So that's what we need to do. We need to plug in 40 thirds for x and 50 thirds for y, and then take the determinant of this matrix. And if it's positive, we found a maximum. If it's negative, we found a minimum, and we should be ashamed of ourselves for getting the wrong answer and assuming it was right. Now, hopefully, if you plug in 40 thirds for x and 50 thirds for y, you will find a maximum. You will find a positive determinant. Does anybody want to do that, or should we just show you the numbers? Just want me to show you the numbers rather than doing it? I mean, I just did a determinant of a 3x3 matrix. If you do need some review over that, like, wait, how do you do that? You know, we have old videos, we have old PowerPoint slides you could look at. But another thing is, I'm okay with you using determinant calculators online for something like that. It might be good to just use it as a check. Like, okay, I'm going to do it by my own, but you know, if I want to have a computer just sort of chug out the determinant for something, you can do that too. So I think it's on the next slide. Plug in the potential solution of 40 thirds and 50 thirds. We get this 0, 5, 2, 5, 100 thirds, 80 thirds, 2, 80 thirds, 0. If you take the determinant of that, I guess you just have to take my word for me. Take my word, it's 400, which is positive, which is a maximum. You guys see how we do that?
Yeah.
Good. Good. I might ask you to do it on Thursday. So I'm glad that you understand it now. I'm reluctant to tell you too much else because then I feel like I'll be pushing other information out of your brain that you don't need for the quiz. No, you're not like that. This is a math class, and we keep building our knowledge base. I would like to say something about how to interpret the Lagrange multiplier, especially when we're talking about consumer theory. I mentioned this in the previous class. I did, but here's a whole slide about it. And that is this: the value of lambda can actually be calculated. You can think of it as another variable. You have two variables that are choice variables, and you have a third variable, which is called a Lagrange multiplier, but it's still like a variable, and it has a value at the solution, right? At the optimal x star, y star, there's like a lambda star, and it happens to be 2/5 times, it happens to be 800 over 9, which is almost 100. I don't know what that is. Like whatever 8/9 is, 90, something like that. This value, how do we interpret lambda? So right now I'm just speaking about economics. This isn't math anymore. I'm really just saying what can an economist take from this particular mathematical tool? And that is, lambda does say something about the additional utility per dollar that can be obtained by the consumer by relaxing the budget constraint. In other words, if I gave somebody an extra $1 and I said, okay, now you can spend this $1 on whatever combination of X and Y you want, how much better off has this person gotten? The answer is that's their additional marginal utility. This is essentially like their marginal utility of wealth, which is kind of an interesting concept as well, because it sort of it takes away the consumer problem, right? I don't even necessarily need to know how you use your wealth, but if I give you an extra dollar, you have more wealth. What will you do with it? Whatever you want. But this term lambda is a sort of a shadow way of calculating how valuable that dollar is to you. But remember, it has similar interpretations using other problems, but I'm really only giving you, for this class, the interpretation in consumer theory. Okay, any questions about that? Good on time, 1:30. Should I do another example here? You think this will help for the quiz if I could do another example? I think so, right? We have 15 minutes. I can do one more example. And this one is a firm who's not doing a maximization problem. It's a minimization problem. And the thing the firm is minimizing it is the cost of production. It wants to produce something, widgets, in as low cost way as possible. And the thing that firms have, the restrictions placed on them, their ability to produce is encapsulated by what's called a production function. And the production function says, if I have this many units of capital and this many units of labor, I'm able to produce this much output. By output, it's like the quantity of goods you produce. That's what output means. So in this case, the square root of K times L is the output that a firm can produce given K units of capital and L units of labor. So if K is 1, L is 1, I would get the square root of 1 times 1 equals 1. I can produce one output if K is 1 and L is 1. If they both double, if K is 2, L is 2, then I could produce the square root of 2 times 2, which is also equal to 2. No surprise here, this is constant returns to scale for this production function. If you know what that means, which I think you should. We talked about that earlier. Okay, but that's not the problem here. The problem isn't determine the returns to scale of this production function. The problem is, what's the cost minimizing way to produce 100 units of output? Well, in order to minimize the cost, you need to know what the cost is, a function for the cost. And I can tell you right now what it is. It's going to be R equals 5. The cost per unit of capital is 5. Side note, that's often R because it's the interest rate. The actual cost of capital is not, if you borrow $1 million, the cost of that isn't $1 million. And you might say, what the heck? Why are you economists just wrong? Isn't the cost of borrowing $1 million $1 million? Actually, no. Assuming that capital is not lost, isn't depreciated, you borrow $1 million, you have the $1 million. The real cost of it is the interest you have to pay on the $1 million. And so that's why R is used as the cost of capital. It's like the interest rate you have to pay per unit of capital. Whatever that is, we'll call that R. And in this example, it's 5. What about the cost per unit of labor? This one makes sense. It's W for wage, right? You have to pay people per unit of labor. There's a certain wage you have to pay them. That makes sense. What's the Lagrangian for this problem? Here's good practice doing a Lagrangian. We may not finish this problem, but let's just get started on it. What do you guys think? Can you tell me, and I'll annotate it right here. I'll give you the first letter. L equals what? It's a minimization, not a maximization problem. Does that affect your Lagrangian equation? No, correct, Jordan. You are correct. And you were able to answer by virtue of your video being turned on. You didn't even have to say anything. You could just shake your head no, and you were correct. You got brownie points with the instructor just by having your video on. Okay. So let's write the Lagrangian. It is what? You may have to unmute to answer this. Oh, by the way, gosh, maybe I didn't. Maybe this is harder than I think. I'm telling you the per unit costs, but am I telling you the total cost? Not really. You have to figure that out yourself. Can anyone figure it out? What's my, first things first, what's my objective function? I'll tell you this, it's not the square root of K and L. K times L. That is not the objective function. The objective is the thing I'm trying to maximize or minimize. And in this example, it's cost. We need a way to measure cost. How do you measure cost? Well, I know the per unit cost of capital is 5. So I take 5 times K. That's the cost of capital, 5K. What about the cost of labor? That's 8 times the units of labor. That's L. So 5K plus 8L. That is the objective function. The thing I'm trying to minimize is 5K plus 8L. Get that? Okay. Now what do? I add the Lagrange multiplier, which is the Greek letter lambda. And I multiply that. That's why it's a multiplier. I multiply that by the constraint, which I still like to write it the right-hand side minus the left-hand side. There really is no right or left-hand side here, but here's the constraint, isn't it? Square root of KL has to be equal to 100. If I want to produce 100 units of output, then that's my constraint. I need to choose a K and an L in such a way that the total output I produce is equal to 100. That's the constraint. So by finding a way to write that in the Lagrangian, I'm just going to say, okay, 100 minus square root of KL. That is the answer to this. What is the Lagrangian? Sometimes just writing out the Lagrangian is maybe the hardest part, getting started in the problem. Figuring out what it is I'm trying to optimize and what is my constraint, and putting them together in this way, that's sometimes not easy, I will admit. But here it is for this problem. You guys have any questions about how I got it? This Lagrangian function? When I said, what is the Lagrangian? I meant the function. You know why it's clear is because it has the suffix IAN. If it has the suffix IAN, I think that means the function. If it's a multiplier, it'll maybe called a Lagrange ending in E multiplier, but because it has an IAN, that's why I meant the function. Okay, let's go on. I'm going to clear my drawings. Scroll down. There it is. Oh, look, I tried to be fancy and do a script L. Okay. It agrees with me. What are the first order conditions? Let's write those. You guys are getting good at this, I bet. What are the first order conditions? Script L with respect to K. There should be one that's running out of space here. I don't know what I'm going to do here. How about the other one I'll let down here? Script L with respect to L. Those are my choice variables, K and L. And of course, there'll be this sort of trivial first order condition, which is script L with respect to lambda. Maybe I shouldn't even try to do script L's, just do regular L's. Maybe part of the reason is L is one of the choice variables here, and I just wanted to make sure you didn't think this L was the same as this L. That's why I went to this trouble of making that script. Okay, what is it? It's just the first derivative, the derivative with respect to K. I'm not even going to wait for you guys to say this. I'm just going to say it. It's too easy. 5. Well, maybe it's not so easy here. Maybe you could use the practice. I'll say plus lambda times the derivative of this, which is what? Anybody want to say? I'll get you started. Negative, because there's a negative there.
So it'll be K over.
There's a 1/2 because it's the whole
yeah.
thing was raised to the 1/2.
Yeah, K over 2 times the square root of KL.
K over 2 times the square root of KL.
Yes. So it's 1 over, so the KO goes to the denominator.
Yeah. Okay, so 1 over this.
Yeah.
Can you see what I'm writing?
Hmm.
This I agree with. Maybe you said that. If you said that, you were correct. There's the negative because of this negative. There's the 1/2 because it's raised to the 1/2. There's the k because of the chain rule. I'm multiplying KL, I'm taking the derivative of what's inside the square root and pulling it outside because of the chain rule.
So
And then I'm reducing the exponent by 1. KL to the 1/2 becomes KL to the negative 1/2, which is like putting a square root in the denominator. So maybe we can write this a little bit nicer to say
I prefer
5. Oh, what were you going to say?
instead of the K, it would have been an L, wouldn't it be? An L.
Oh, because we're doing K right now.
Yeah.
You are correct. Sorry, guys. Thank you for catching that. Aren't you the one who said K, or did I say K?
Yeah, I said K. You just followed.
Okay. Well, we both didn't notice it, but
Yeah.
you're right, because we're taking the derivative with respect to K. That means once we churn out the chain rule term here, it won't be a K. It won't be a K. It'll be an L that comes out. So that is correct. Thank you. Maybe I can combine all of this into one fraction, and that's negative. Ooh, can I be fancy here? I'm going to show you some fancy algebra here. There's an L on the top, and there's a square root of L on the bottom. L divided by the square root of L is the square root of L. And therefore, I can just even put that inside this square root and say just the square root of L over K if I want it. But there's still a lambda over 2 minus lambda over 2 times the square root of L over K. Is that too fancy? Maybe it's not even that helpful. But that has to equal 0. Another way to make it equal 0 is just to say the negative side equals the right side. I can change that to an arrow. I think that's a good first order condition here. You know what you do in a lot of these problems is solve for lambda. So let's go like one step ahead here and start solving for lambda. I don't think I'm going to finish this problem before the end of the class, but we'll see how far we get. Lambda equals, move this over, it'll be 10. Lambda will actually be equal to 10 times the square root of L over K. Once I move it to the other side, it becomes the reciprocal. It becomes the square root of K over L. Is the denominator and the numerator flip. I think that's what we get. You guys agree? How about for this one? Kind of for the same thing is happening here. 8 plus lambda negative 1/2 K times 1 over square root of KL. That becomes 8 is equal to, okay, same thing's happening here. We have lambda over 2, except now instead of square root of L over K, this K is in the numerator, and that becomes square root of K over L. And then lambda equals 16. Let me turn it from here. Lambda equals 16 times square root of L over K. I like to write it this way because now we can eliminate lambda. I'm sorry, there's so little room here. Hopefully you can see, but I'm running out of time. Yes, I'm running out of time. But what's the idea here is I'm going to eliminate these two lambdas by setting this equal to this. I'll get something like, divide both sides by 10. I'll get 16 over 10 or 8/5. Sorry, let me just write it. I'm come this far. I feel like it might be worth it to finish it. Something like 10 over KL equals 16 square root of, I'm running out of space here, L over K. And if I multiply both sides by, let's say, the square root of L, I'll have a positive L on this side, and this one will go away. If I multiply both sides by the square root of K, I'll have a just regular K on this side, and this one will go away. I essentially get 10K equals 16L from this expression. 10K equals 16L. And now to solve it, what I will do is I will plug that back into the constraint, because the constraint, if as you recall, will always be the third first order condition will just give me this constraint back. But I plug this in here into that, and that will be the way I solve for K and L. I'm not actually going to do it. Maybe I'll show it the answer to you guys in the next class, but at least conceptually, that's how you would solve this problem. I liked this problem because it's not a simple constraint. Most of the constraints I've been giving you are just something plus something equals something. This is a little more complicated of a constraint. And so maybe on the quiz, you should be prepared for the potential of a constraint which isn't just linear. If it's not linear, that's okay. You just take the derivatives of it and use it to turn out your answer as if you were doing any other type of problem. You guys have any questions about that before we end class? The Lagrange method for solving constrained optimization problems. I think it's good to know. It's good to know, even if you don't end up using it a lot, but it sort of puts a lot of pieces together in your math, econ math toolbox. Okay. Well, we will do a little bit more next class and then do the quiz. And I'll let you know when your next homework assignment is going to be, probably not for a week at least. So good luck, guys, and I will see you Thursday. I should stop recording.
Thank you.